Good morning to you all. Welcome to the class. So let us go with another type of problem in the bracket connection design. So the problem is like this. A 12 mm thick bracket plate connected to the flange of the column ISHB 350 as shown in figure. The size of the weld is 8 mm. Check the safety of the joint. So take Fe 410 material for the steel plate. See, look here. This is the bracket plate and this is the I section column. Okay, and this is the flange of the column. Okay, and this bracket plate is connected to the flange using 8 mm size weld. Okay, and the load 150 kilonewton is acting at a distance of 150 mm from the face of the column. So these are the details given. Service load given is 150 kilonewton. Therefore, PU equal to, that is the ultimate load or design load or factored load, equal to 1.5 multiplied by the service load, that is equal to 225 kilonewton. And for the weld material and the plate material, we take the value equal to 410 Newton per millimeter square. Of course, weld size is 8 millimeter. So once the weld size is 8 millimeter, the thickness of the throat equal to 0.7 times the weld size, which is 5.6 millimeter. Here, so the problem says we need to check the safety of the weld. Okay. It says check the safety of the joint. That means check the safety of the weld. So what we do is, everything is given here. Size of the weld is given. Okay, length of the weld is given. The service load is given. And all the related dimensions are given and other measurements are given. So we have to check whether this bracket along with this weld can withstand a service load of 150 kilonewton. So when we say service load of 150 kilonewton, it has to be safe for a design load of 1.5 times 150, that is equal to 225 kilonewton. So as we discussed in the previous problems, if you look here, we have to check the area of the weld which is subjected to maximum shear stress. Okay, so what is the maximum shear stress weld area? First, we are going to find out the location of the neutral axis. So from the center neutral axis and the centroid of the weld, once you find out the centroid of the weld, find out the weld area which is farthest from the centroid. So that is going to be subjected to a maximum shear stress. So we have to check what is the actual shear stress developed. And we have to make sure that that value is less than the design strength FWD of the weld. Once that maximum shear stress is less than FWD, then we can say the joint is safe. So what is the maximum shear stress that is going to be developed? That is F value. First, we need to find out the F value. So you know how to find out all these values. So that is find F1, F2 and theta. Once you find out these values, automatically you know what is going to be F. So first, let us start with the value of F1. Of course, the unit of F1 is Newton per millimeter square. So F1 equal to PU divided by the throat area. Throat area is total weld length multiplied by the throat thickness. So what is the total length of the weld? So that is 200 plus 200 plus 400. So that is 800 multiplied by 5.6 will give you the throat area. So PU divided by the throat area of the weld will give you the direct shear stress of 50.22 Newton per millimeter square. So that means the direct shear stress will be acting like this downwards. Is it clear to you? So, and the F1 value is constant throughout the length of the weld. Okay, each unit area of the throat is going to be subjected to a direct shear stress of 50.22 Newton. Okay, so the next point is to find out what is F2. So we have the formula for F2 PU E divided by IP multiplied by R distance. Okay, PU is given. We need to find out the eccentricity and the polar moment of inertia, and of course this is the R distance, that is the distance of the farthest weld from the centroid. So first thing we need to do is to find out the location of the centroid of the weld. So we know this weld is symmetric about XX axis, and it is the centroid is lying somewhere along this axis, and we need to find out what is the distance at which the centroid is located. That means we need to find out X bar. So we are going to find out what is X bar. Okay, from here, remember, from this line. So for that, what we do is we are going to take moments of all the forces about this axis divided by the total area of the weld throat, or total throat area of the weld. So let us consider the moment of this area about this axis, that is given by 200 multiplied by the throat thickness, which is 5.6, multiplied by 200 by 2. That is the location of the centroid of this weld of 200 millimeter length is located at a distance of 200 by 2, that is 100 millimeter from the vertical axis. So that's why I have written 200 by 2. So we have two such welds, one is at the top and the other is at the bottom. So that's why I multiplied the value by 2. Plus there is one more weld area here, that is 400 is the length multiplied by 5.6 is the throat thickness. And here we are not going to take 4.2 by 2 because it is a small value. We are going to consider the distance between the centroid of the vertical weld and this edge line as 0 divided by total throat area 200 multiplied by 5.6. Okay, will give you the throat area on this side multiplied by 2 because we have two such welds, plus 400 multiplied by the throat thickness here will give you the total area of the throat. So after doing the calculation, X bar equal to 50 millimeter. So that is the location along x-axis wherein the centroid is located. Okay, so that means go for a distance of X bar equal to 50 millimeter. There you draw a line parallel to this reference line. Wherever this line and the vertical line meet is the location of the centroid. Okay, so once you find out the location of the centroid, so eccentricity of the lobe is always measured with respect to the centroid. So how do we measure? So continue the line of action of the load PU, and from the centroid draw a line perpendicular to this line. So whatever the perpendicular distance is the eccentricity. Okay, so here what is the eccentricity value? So from here it is 200, because this is 200, this should be 200, plus 150 will give you 350 minus of X bar. So that is 50, that is 200 plus 150 minus 50, that is equal to 300 millimeter. So that is the eccentricity of the lobe. So due to the eccentricity of the lobe, the weld is subjected to direct shear as well as the shear due to torsion or twisting moment. So shear due to torsion we are going to represent by F2. So we need to find out what is F2. So we know this one E, the eccentricity 300 millimeter. Okay, then what is this R distance? R distance is the distance from the centroid to this place. Okay, that is the radial distance we are measuring. So that can be calculated. So if you consider this triangle, okay, so this distance is known, that is 200 minus of x bar, that is 50, will give you this distance, that is nothing but this distance. Drop a line here. Okay, this distance is going to be 400 by 2, that is 200. Once you know these two distances, so in this right angle triangle, we can find out what is the hypotenuse, and this hypotenuse is the distance r. Okay, so next thing is IP, that is the polar moment of inertia of the weld. So what is the polar moment of inertia? That is the sum of the moment of inertia of the weld about x-x axis and y-y axis. That is IP equal to Ixx plus Iyy. So we'll find out what is Ixx and Iyy one at a time. Okay. So Ixx, that is the moment of inertia of this weld about this axis, is given by moment of inertia of this weld about its own parallel centroidal axis, that is 200 multiplied by TT cube, that is 5.6 cube divided by 12. 200 multiplied by 5.6 cube divided by 12, plus, because I am applying parallaxis theorem, area of this weld, that is 200 multiplied by 5.6 multiplied by square of the perpendicular distance between these two lines or between these two axes, where xx is the main centroidal axis and this axis is the axis passing through the centroid of this area of the weld. So that distance is 200. Okay, 400 by 2. And distance square, that is area of the weld multiplied by the distance square. Okay, and multiply the whole thing by 2. Okay, so because we have two such welds, I think I've forgotten to find out, multiply this by 2. So as of now, let us take this value. I'm going to correct it later. Okay, so multiply that value by 2 to incorporate this one as well, plus moment of inertia of this weld about this axis, that is 5.6 multiplied by 400 cube by 12. 5.6 multiplied by 400 cube by 12. Here I am not applying any parallaxis theorem because the centroidal axis of this weld group is coinciding with the horizontal centroidal axis of this weld. So that way there is no distance between the main centroidal axis and the individual centroidal axis. So that's why I've taken only this value. So as I said before, 5.6 cube, that is smaller number cube, will end up getting some number which is not so significant. Okay, we can ignore this. Even if you include this, I don't think it makes difference, but develop the habit of ignoring these small numbers. So finally, I got Ixx value equal to this much. So please check the calculation line. Next, similarly, Iyy value, that is the moment of inertia of this weld about this axis, that is given by moment of inertia of this about its own centroidal axis. So the own centroidal axis, now they should be parallel to this. Okay, that is given by 5.6 multiplied by 200 cube by 12. That is 5.6. Okay, multiplied by 200 cube by 12 plus area of this weld, that is 200 multiplied by 5.6 and square of the perpendicular distance between these two vertical axes, which is 100 minus 50. So that is 200, 5.6, 100 minus 50 square. Okay, and we have two such welds, that's why I have multiplied the value by 2. Okay, plus there is one more weld here. That is moment of inertia of this weld about its own central axis. That is this multiplied by 5.6 q by 12. 400 multiplied by 5.6 q by 12 plus area of this weld multiplied by the square of the perpendicular distance between this axis and this axis, which is 50 millimeter. So that is 200, sorry, 400 multiplied by 5.6 and 50 square. Okay, finally, I got the value of Iyy equal to 18.66 multiplied by 10 to the power of 6 millimeter to the power of 4. So once we have those two values, add those two values to get IP value, that is the polar moment of inertia. Okay. Next, regarding finding out the value of R from, that is the distance from here, the centroid, to the tip of the weld, where that weld is going to be subjected to highest stress. I have done the calculation here. Okay. Here. So this is 150 and this is 200. So this is a right angle triangle. So I got this R value as 250 millimeter. So coming back to this formula, F2 equal to PUE divided by IP multiplied by R. Now I know all the values for this equation. So by substituting the values, I can get the value of F2 equal to 122.17 Newton per millimeter square. Once that is done, the next thing is to find out what is angle theta. So when this is angle theta, of course, this should be theta. I explained yesterday in the previous class. Okay, how to get this, how this angle is equal to this angle. Okay, so find out what is this angle theta from this triangle. Say tan theta equal to opposite side, which is 200 divided by adjacent side, that is 150. So therefore theta equal to 53.13 degree. So once we have the values of F1, F2 and theta and substitute the values in this equation, that is in this equation, which you are familiar with already. Okay, after substituting the values here, I got the value of F equal to 157.51 Newton per millimeter square. So that is the resulting shear stress this critical area of the weld, critical unit area of the weld is subjected to. Okay. Similarly, there is one more weld here. One more tiny bit unit area of 1 millimeter by 1 millimeter, which is going to be subjected to the same shear stress. So any weld further inside, the stress F value is going to be less. So here we get maximum value. Okay. So F equal to this much. Then this is the stress developed in the critical weld due to the design load of PU, which is equal to 225 kilonewton. Okay. Let us find out what is the design strength of the weld. As per 10.5.7.1.1 on page 79 of the code book. So by assuming the welding is being done at this site, we can take gamma MW equal to 1.50. Therefore, FWD equal to FU by root 3 multiplied by 1 by gamma MW. So we know this formula from the code book. Substitute the values. So we get FWD equal to 157.81. So what it means is, so this is the design stress developed at the critical weld and this is the design strength. So actual design stress developed is less than the design strength. Okay, then our joint is safe. In case F exceeds FWD, what it means is our design strength of the weld is less than the design stress due to the design load, then the weld is going to be unsafe. So in this case, fortunately, we got the value very close, and of course, F is less than FWD safe. So if you correct this mistake, which I forgot to multiply this value by 2, so once you correct this mistake, I think this value will go down further. Okay, so that is F value will go down further. So this completes the problem. Therefore, the provided welded joint is safe. You can declare that with that sentence, then you can end. Okay. So coming back to the next problem, this is a little bit tricky. Listen carefully for this problem. So a bracket plate is used to transfer the reaction of beam to a column flange of ISHP 300. A fillet weld of 6 mm is the weld is used to connect the plate and column flange as shown in figure. This is a bracket plate of certain thickness, okay, and this is the flange of the I section. This is one of the flanges. There is another flange on the other side, okay. Find whether the connection is safe or not. Okay, we have to find out whether the connection is safe or not. Again, how do we find out whether the connection is safe or not? So we are going to take out the area of the weld which is subjected to maximum shear stress, and we are going to compare that value with the design shear strength of the weld. Okay, that when that value is less than FWD, then we can say the joint is safe. Okay, so there is a beam coming on this bracket, and that beam is transferring a load of 120 kilonewton at an angle of 30 degree with respect to the horizontal. This is not vertical, remember. Okay. Next, weld size, of course, given, that is equal to 6 mm. Therefore, throat thickness is equal to 0.70 times 6, that is equal to 4.2 mm. So what is service load? P equal to 120. Therefore, PU equal to 1.5 multiplied by 120, that is equal to 180 kilonewton. The first thing, as usual, we do is to find out the location of the centroid of the weld. Of course, this weld is symmetric about the x-axis axis. So the centroid is lying somewhere along the axis of symmetry. To locate the centroid, we need to find out x bar from this reference line. So we can find out x bar by taking moments of all the weld areas divided by that moment by the total area of the weld, like this. So we can find out what is x bar. We got the x bar value equal to 66.67 millimeter. Okay. Next. So we got this value as 66.67. Careful here. So this is 200 millimeter given. See here, 200 millimeter. This is 200 millimeter. This is 200 millimeter. Okay. So once this is 66.67, this should be 200 minus of 66.67, that is equal to 133.33 millimeter. So this distance is that. So if you draw a vertical line here, extend this, so this distance is going to be the same thing, 133.33 millimeter. The next thing is this load is acting at an angle of 30 degree. That means it makes an angle of 30 degree with respect to the horizontal. If you extend this line, this is also 30 degree because these two are vertically opposite angles. Okay. Next, if you consider this triangle, okay, so you know this. So this is 30. We can find out what is this distance, that is AB. Tan 30 equal to AB divided by BC. That way we can find out what is AB. So I got the value of AB equal to 134.70 millimeter. So once you have AB, okay, so we can find out what is AG. AG is AB minus BG. What is BG? 200 divided by 2. Okay, that way AG equal to 34.70 millimeter. Then why do we need that AG first of all? Because when you need to find out the eccentricity, as I said, the eccentricity is measured by drawing a perpendicular line from the centroid to the line of the load or to the line of action of the load. That means because this is inclined, so extend this line from G, draw a line perpendicular to the line of action of the load. So actually this is eccentricity we need to find out. So to find out this eccentricity in this triangle, we need AG. That's what I did. I found out AG value, which is 34.70 millimeter. Okay. So AG is 34.70 in this triangle. So this is 60 degree. How did we get? So consider this triangle, that is ABC. This is a right angle triangle. This is 90. This is 30. So obviously this should be 60 degree. Once you know this 60 degree, once you know this value, you can find out what is GD value, which is the eccentricity value. That is sine 60 equal to opposite side by hypotenuse. So here sine 60 GD by AG. So GD is nothing but the eccentricity. Again, remember, eccentricity is the perpendicular distance drawn from the centroid to the line of action of the force. So in the previous examples, the load was vertical. There was no problem. Okay. Again, just in the previous examples also from G, we used to draw a line which was perpendicular to the line of action of the force. Same here. Okay. So once in this triangle, sine 60 opposite side by hypotenuse. Hypotenuse is known 34.70. Opposite side is GD, that is the eccentricity which we don't know. So after doing this calculation, we got the value of E, that is the eccentricity equal to 30 millimeter. Okay. So eccentricity 30 millimeters. Keep those values aside for now. Now coming back to this formula. Of course, these calculations can be done under F2 calculation. That is, see here, to calculate the shear stress F2 due to torsion. So under this, you can do all these calculations if you want. That is your choice. So coming back to this formula, F equal to square root of those values. Okay. So let us find out one at a time. F1 equal to PU divided by the throat area. So what is the PU value? P is 120 kilonewton. Okay. So PU value is 1.5 times 120, that is 180. So 180 multiplied by 1000 to convert the value into Newton divided by the throat area. Okay. So 200 multiplied by 4.2. Everything is 200, 200, 200, 200. So 3 times 200 multiplied by 3 multiplied by the throat thickness will give you the throat area. So design load divided by the throat area will give you the design stress F1 in Newton per millimeter square. Next. So to calculate the shear stress F2 due to torsion or twisting moment. So PU is known. E we calculated here. If you wanted, you could have moved this under F2 calculation. Okay, but somehow I calculated already above. So E is known. Next. So R can be calculated by looking at this figure. the way we did for the previous example. Once X bar is known, can we not find out the R value here? So that is also done here, which is equal to 166.67 millimeter. So in this equation, another thing we need to find out is IP, that is the polar moment of inertia of the bolt, of the weld, and IPP or IP equal to IXX plus IYY. So again, apply parallel axis theorem about the horizontal axis, find out the moment of inertia of the weld about the XX axis. So the way we did for the previous examples, finally I got the value of IXX equal to this much. Similarly, IYY equal to same thing. So again, that is the moment of inertia of the weld about IYY axis, which is passing through the centroid, of course. So I got the value of IYY equal to this much. So I'm going to add these two numbers. So once I added those two numbers, I got the value of polar moment of inertia equal to 30.60 multiplied by 10 to the power of 6 millimeter to the power of 4 IP. Okay. So once IP is calculated, so substitute all the values in this equation, and find out what is F2. So that's what done is here. Okay. And so F2 value is 29.41. And theta, what is theta? That is the tricky part here. So we'll have two theta values in this, because we have two weld areas which are located at the R distance. In this case, both unit areas of the weld at a distance of R from the centroid are not going to be subjected to the same kind of shear stress. Only one of those two areas is going to be subjected to highest resulting shear stress of F. Okay, so what is that area of weld? See, in the previous examples, I will go back to the previous example with the vertical load. So in case of this, with the vertical load, this weld area, unit area of the weld here, and unit area of the weld in this, both of them are going to be critical, and they are going to be subjected to the same maximum shear stress of value F. But in this case, because the load is inclined, these two welds are not going to be subjected to the same shear stress. One of them will be higher than the other. So what we have to consider is the value which is higher. Okay. So as far as F1 and F2 are concerned, okay, fine. They are going to remain the same here and here. Here F1 is same as F1, here F2 is same as here F2. But when you club those two and find out the resultant of those two forces, that is, if you find F value, that is the resultant, then which one will give you the highest value of F, whether here or here? So what it means is, if you take certain value of angle theta, as theta increases, cos theta value decreases. Remember, so as theta increases, cos theta value decreases. For example, what is the value of cos 0? It is 1. So what is the value of cos 30? It is root 3 by 2, that is 0.866 by 2. So what is the value of cos 45? It is, so what is, then it is 0.707. Okay, so cos 60 is half, cos 60 is half. Next, Cos 60 is, sorry, some value. And what is the value of cos 30? Again, it increases, decreases. Okay. So what I mean to say is I'm just mixing up those values. And in case of sine theta, as the value of angle theta increases, the value of sine theta increases. Okay, sine 0 is 0, sine 30 is half, sine 45 is 1 by root 2, that is equal to 0.707, and sine 60 equal to 0.866, and sine 90 equal to 1. But in case of cos angle, so cos 0 is 1, cos 30 is 0.866, okay, cos 45 is 0.707, cos 60 is half, cos 90 is 0. Is it not? So here in this case, F1 and F2, F1 and F2. So if I take F1 here, F2 here, what is the angle theta? This is the angle theta. So if I take F1 and F2 here, what is the angle theta? This is the angle theta. So out of these two, this is going to give lesser value. Once it gives lesser value, then cos theta is going to be more than cos theta here. Is it not? So if you substitute that value in the above equation here with lesser value of theta for cos, then we will end up getting higher value of f. That means, so this is the weld area which is going to be subjected to highest stress even when compared to this. So this is the critical area of the weld. First of all, if at all the weld fails due to this load, it fails or it starts failing from this point, not from here. Now we'll find out what is the angle between F1 and F2 and F1 and F2 in both cases. So if this is PU, okay, so F1 value, that is the direct shear stress, is going to be parallel to this PU value. Always remember, direct shear stress F1 will be parallel to PU value. That means if I extend this, this is 30 degree. Similarly, F1 is making an angle of 30 degree with respect to the horizontal. Okay. Next, this is 36.87. How did we find out 36.87? Say this is called tan theta 1 equal to opposite side, which we know 100 millimeter, divided by adjacent side, which is 133.33. So after finding out theta 1, 36.87. That means, so if this is 36.87, this is parallel to this, and this is the line cutting these two lines. So this angle is equal to this angle because they are alternate angles. Is it clear to you? This is alternate angles. So this is 36.87. If you look here, F1 is 30 degree with respect to the horizontal. Therefore, the angle between this line and F1 is going to be 36.87 minus of 30, which is 6.87. This angle is 6.87. Okay. Plus, this angle is 90 degree. So the total angle is 90 plus 6.87, 96.87. If you take cos of 96.87, so that is going to become minus sign. Okay. That will reduce the value of f. Okay. So this always acts perpendicular to this line. Similarly, if you consider unit area of the weld here, again, this F1 is acting parallel to this load. That means this is making an angle of 30 degree with respect to the horizontal. Okay. And this F2 is perpendicular to this. We discussed about this. So when this is acting like this should be acting in the F2 should be acting in the clockwise direction as well. So this F2 is making an angle of 90° with respect to this line. Okay. So when this is 36.87, this should be 36.87° as well, because they are alternate angles. So once you have 36.87°, okay, so this is 90°, so this is 30°. So 90 minus of 36.87 minus of 30°. Look here. So we got the value of theta equal to 23.13°. So that is the angle between F1 and F2 is equal to theta, which is equal to 23.13°. Is it clear to you? So out of these two, so we will get higher value of F when you take this angle theta, that is 23.13°. I hope this is clear to you now. So just you, when you are at home during evening time, open this and draw a figure, neat figure on your own and analyze it once. Unless you analyze it, you cannot get it. Okay. So once you understand the concept clearly, okay, it will be easy for you. So coming back to this, theta is the angle between F1 and F2. So that theta should be used in the formula to find out F. So this is theta 1 equal to 36.87. So that is theta 1 equal to opposite side 100 divided by 133.133. So that is equal to 36.87. This is where I calculated. Okay. So theta is the angle again. So this is the angle I am going to make use of. Okay. So theta equal to this much. Now coming to this formula, F equal to square root of F1 square plus F2 square plus 2 F1 F2 cos theta. So by substituting theta equal to 23.13 this equation, we get the value of F equal to 99.15 Newton per millimeter square. That is the stress or design stress developed at the critical area of the weld here due to the design load of PU. Okay. So any weld along this or any unit area of the weld along this is going to be less than this value. The highest shear stress is 99.15. Again, that is going to be occurring in this area of the weld. Okay. Next, so to check whether the joint is safe or not, so we'll find out what is the design strength of the weld. So what is the design strength of the weld? So this is the design strength of the weld, that is equal to Fu by root 3 multiplied by 1 divided by gamma mw. So Fu is 410 root 3 multiplied by gamma mw by, if nothing is given, assume whatever you want to assume. You can assume field weld or sharp weld. So if it is sharp weld, you take gamma mw equal to 1.25, and if it is field weld, you take gamma mw equal to 1.50. So if nothing is given, on safer side, I'm going to take this value as the field weld. That way, that value equal to 1.50. So FWD equal to 157.80 Newton per millimeter square. So actual maximum design shear stress developed is less than the design shear strength of the weld. Therefore, the connection or the joint is safe. Okay, I hope this is clear to you guys, and this needs some attention from your side. Okay, So please concentrate on that. Just as I said, practice it a little bit. Anyway, you have the notes with you. Okay, and you have the video here. Okay, refer both. And if at all you get any doubt at any time, you can always come back to me so that I can clarify it. Okay, so with this, we completed the bracket connection type 1. So this is going to be type 2, which I'm going to cover in tomorrow's class. So I cannot cover in today's class because we are only left with some 6 or 7 minutes. So I don't think I can even start this. So, okay, guys, you can drop off. Thank you very much and be safe. And I'll see you tomorrow. Thank you.